Good? Okay. All right. Hi, everyone. My name is JF. Talk today is much ado about noping. So let me tell you about this. Okay. There we go. Let's get started. So let's start with a question. Who here knows assembly? Raise your hands. Audience participation. All right. Most people. Nobody's asleep. Great, thank you. So don't worry if you don't know assembly. I'll show you a lot about assembly, but I'll explain all of it, right? So it won't be that bad. I'm going to try to explain a bunch of stuff. So, but first, see what happened. Like, I asked a question, and I got you to do something. You raised your hand just by giving instructions, right? So I asked a question, and look, you all raised your hands. So that worked pretty well, right? So what is that? It's a program. You executed successfully for me. So let's try again. Can you say hello world? Thank you. Let's try again. And everyone on YouTube should say hello world as well. Okay, so that worked really well. The program linked, it loaded, it ran. So I had a program that did a thing. Very exciting. Okay, so let's try something else. I'm going to begin the talk, and I'd like all of you to do nothing during the talk. All right? Nothing. Can you do that? No. But I want you to be idle. Like, I want you to do nothing. Right? And it's super awkward, right? So it makes you feel self-conscious. Do nothing. Like, what is that? But when you sat here, most of you, the hecklers were planning to do something, but the rest of you weren't planning to do anything during the talk, right? While I talk, you're not supposed to be doing anything. So brief recap. I ran a program to answer a question, and I had a program to print a greeting, and that's the same thing we do with computers. And now I'm trying to have a program that does nothing, right? The audience should do nothing while I do the talk. That's what I'm trying to do here. And that's what my talk is about. What does a computer do when you ask it to do nothing? It's a serious question, I promise. Right? But it's a really interesting question if you start digging into it, and we'll do that for the next hour. So surely, like right now, you're all doing something, right? Even if I asked you to do nothing. Right? So the phone's in your pockets. Mine's here, right? It's not in my pocket, but it's here. It's probably doing something right now. I'm probably getting text messages or whatever. I hope you didn't ask your phones to do anything during the talk, but I bet they're still doing something, right? So phones do something, computers do something, even when they're supposed to do nothing. So let's dive into that. All right. Okay. So those of you who know assembly, who raised your hand, have probably figured out by now from the title and the hinting and whatever else that the talk is about the NOP, right? Okay? So today, we're going to talk about the NOP, the no operation, right? So it's a beautiful little rendition of what a NOP might look like. All right, so maybe a quick definition of what a NOP is. A no operation instruction, literally an instruction that does nothing, right? Fairly straightforward. What is it good for? Why would I use a NOP? Is that a thing in a computer? Why? Right, so let's look at a NOP in the wild. So I have a program on the left, says hello world, just like you did a few minutes ago. And then on the right, I have assembly. And third instruction from the bottom, right there, we have a NOP. This is x86 code. There's a NOP. Good. So if you go on godbolt.org or whatever, and you type this in, you'll get a NOP, most likely. So it's a thing that we see in the wild, happens all the time. Why do we do that? Why do computers have NOPs? Well, first let's start. How do you even spell NOP? Is it like NOOP, N-O-O-P? Is it NOOP with a dash? Is it like capitals, lowercase, all uppercase or something? And what does it do? What do you think a NOP does? Nothing? Huh? Fancy the address counter? Yeah? Maybe. Yeah, erase the next instruction. Let's see it. I can probably EAX to EAX. Nice, nice, nice. So those of you who didn't raise your hand about assembly, I see you frowning right now. You're like, what is he talking about? Well, why do you even want to not frowning? What is that? But see, I thought I asked you to do nothing, and you're like scowling, right? So already that scowl kind of has a side effect, right? It's still technically doing nothing. Your scowl doesn't really serve a purpose, but your facial expression is sort of a kind of side effect that we have. And when a computer does nothing, what's the desirable side effect for doing nothing? Surely you wouldn't put a NOP instruction in a computer if you wanted it to do something while you do nothing, right? So in some cases, you might want the instruction to be aligned to a certain modulo. I'll simplify that and say align your code to a cache line. It's not quite right, but you can think about it that way. You might use a NOP for padding to cause the alignment that you want, right? That's a good example of what you might want to do, and I have a little illustration that tries to show that. Another reason, no trolling, please. Another reason is in older computers, think like classic game consoles and stuff like that, programmers inserted NOPs to deliberately delay the execution. Right? So back then, the instructions kind of executed in order, and you could predict, the manual told you this instruction takes this long, that one that long, that one that long, so you could predict exactly what's going to happen, and you might want to synchronize like the sprite going around the screen and the sound and other stuff, and so you would put NOPs to have that precise timing. That's a good reason to have NOPs. And sometimes you leave NOPs because you want to come in and patch the code later, right? So your compiler might do that or something like that. The linker could come in and patch the code. You might want to debug, do aspect-oriented programming. You might want to add a call function or something in the middle of your code. And so the NOP is useful for that. You might want to have a breakpoint, right? So if you don't have a hardware watch point, breakpoint, something like that, you might put a NOP and then change it to a breakpoint during execution to break at a certain part of your program. Those are all valid reasons to have an instruction that does nothing, because it might be useful to do something else. It has a side effect. Right? Makes sense. So now I hear some of you saying, the NOP, right? That's a good start, but like I'm sure already we have like angry people on YouTube preparing to comment like, hey, there's more than just a single NOP. Like, and that's fair, right? I asked you to do nothing and you had a side effect of going on YouTube and like putting a comment that has zero impact. That's fine. It's a side effect, right? That's fine. But like, I gotta say, like, Rando Programmer 256 here has a good point, right? There's more than one type of NOP. There's more than one type of instruction set architecture, right? You mostly know x86, you know ARM, things like that. There's a bunch of others, and each of them tends to have multiple NOPs. All right, so now some of you are laughing at computer designers or at Bryce's comments or something like that. But like, if you're laughing at computer designers, you're like, they had the computer doing nothing, but they had the computer doing different types of nothing. That's really funny, and it's a fair observation, right? Now, it seems ridiculous to have many nothings for a computer, but consider a written language or spoken language, right? There's so many types of nothing in written or spoken language. In a written language, you have like a space in the blue on the left, you have the comma, the semicolon, the EM dash, the period, and like they provide delineation to what you say, but they are a type of nothing. Right? So if you're laughing at the computer developers for having NOPs in their stuff, well, like you use NOPs all the time when you write. Well, most of you, I assume, right? So, and like all these spaces and dashes and commas, they have a different meaning, different types of NOPs, different types of nothing in your language, right? So it kind of makes sense. And so in French, we have many silent letters in words, right? Vestigial letters or something. And so my native language is French. I try to teach French to my kids. And I like teaching French really shows you how ridiculous it is as a language. So tell me, everyone, like, how do you pronounce that word I have on the screen? Yeah? So like, I lived in the US for like a dozen years, and Americans, like Robert and whatever, will say croissant, right? At the end. It's a silent T. Like, why do you guys do that? What are you trying to do? Is it like a female croissant that you want? Like, yeah, it would be a croissant in French, but everyone knows that croissants are like masculine in French, right? So, le croissant. Like, that's how you pronounce it. So look at that word. It has so many useless letters in it, right? Like, if you've ever spoken French, like, and you're surprised at NOPs, your whole language is full of empty things that mean nothing, right? And it's not just pastries. Here's how you write birds in French, right? How do you pronounce this word? Like birds, plural. This is the word in French. How do you pronounce it? Yeah, pretty good, pretty good. So, like, how many of the letters in that word are useful? So for those who don't know, the way you pronounce this word, birds in French, is oiseau. It's basically like 2 syllables, right? It doesn't make any sense. If you write it out, you just have to know how to write it. And so, NOPs kind of make sense in that retrospect, and every other language has weird stuff like that, right? So where was I? Language is silly. Right? And so we'll talk about silly things, not just in languages, but in a bunch of other things, including programming languages today. Let's start with ASCII. So, computers really embrace the silliness because we're human, we create languages, we created programming languages, everything hardware. And computers have code for silence or blanks, as I showed you earlier, right? So this is ASCII. It's how computers represented characters in ye olden times, right? And I have all the ASCII characters on screen right now. It started with null, and it has a bunch of other stuff, including white space characters, right, shown on screen. Right? There's 6 of them right now highlighted. And imagine, like, you're the designer of ASCII, and you're like, I have 128 things that I can put in there. I'm going to put 6 nothings in there, right? Like 6 blank, not even commas, whatever, like blanks. That's a high percentage of nothing, right? That's kind of surprising, right? So nowadays, we have more than one language in the world, and so we use Unicode. Unicode's basically taken over. And do you know how many white space characters there are in Unicode? Yell it out if you know. How many? Because Unicode can be pretty long, right? How many white space characters are there? They're all on screen. You can just count them. All right, that's right. So there's 25 white space characters in Unicode. I put them on screen here. And like, it's fascinating the stuff there is. Of course, there's the 6 from ASCII, but there's a bunch of other ones afterwards. And like, 6-figure space? I'm sorry if this is your language. I have no idea what your language is doing with 6-figure space. I don't know what that is, right? Yeah, it's like nothing. I don't understand. So computers have different NOPs and vestigial NOPs, and it doesn't seem so silly after all. With all the stuff that I've shown you already, the computers have NOPs, right? That's interesting. So today, I'll tell you about many, many NOPs, and all of them will be more useless than the next. They'll be very exciting. Or at least they claim to be useless. We'll see if they are. So I'd like the help from the audience, especially the folks in the front here, to count all the NOPs that we have. So already, I've shown you 1 NOP in assembly, right? The one that was in Rainbow, kind of from Hello World. 25 in Unicode, 6 in ASCII. I'll double count here, but 6 in ASCII, 2 in French, and 1 on YouTube. 1 NOP on YouTube. So we're already at 35 NOPs, right? So I'd like you all in the front to keep a count of the NOPs we have and yell them out from time to time. Okay, so let's start with ARM. So I mentioned ARM earlier as an instruction set architecture, and we'll consider that first. So it's very common. There's ARM everywhere these days. My phone and laptop have them. Spoiler alert, they have many ways of doing nothing in ARM. So on modern ARM CPUs, the NOPs disappear in the front end, right? So you have a decoder for the instruction, and the front end is what decodes the instructions and figures out what to do, and then it queues them in an execution queue. And on ARM modern computers, the decoder just looks, says this is nothing, and throws it away. It doesn't enqueue anything. Okay? So ARM v8, what's in most phones and laptops and whatever else, the NOP instruction is encoded as like this. So ARM has 32-bit instructions for every instruction. ARM v8 does. And so this is the encoding. On the top row, you see the bit number, and on the row under it, you see the bit for every position, and then you see the encoding. If you go on the ARM manual, the ARM reference manual called the ARM, it's very cute. There's a CRM thing there underneath where all the bits are set to 0. So this is an instruction encoding that they show you. Very beautiful. And so clever readers will notice that the field has a bunch of zeros in it, and that's because the way ARM encodes its canonical NOP in ARM v8 is actually an alias for the hint 0 instruction. Right? So that CRM is the 7 bits represents a hint, and when you hint at 0, you're hinting at nothing. And there's a bunch of other hint instructions that exist that hint at other things that do nothing because they're hints, right? So already there, for the counters in front, we've got 7 bits worth of NOP that we've just discussed. Okay, so please increment the counter like that. So that's very exciting, and I'll talk about the hints a bit later. ARM v7, which was the version of ARM that came before it, fairly different. Most of the instructions are different except for the SIMD, the neon instructions. But ARM v7 had different encoding. And the 32-bit instructions and Thumb2, which mixed 16-bit encodings and 32-bit encodings for instructions, each had NOPs. In Thumb2, the NOP was 16 bits, the regular NOP, and then NOP.W was the wide 32-bit NOP in case you wanted extra wide nothingness, right? So ARM32 encoded every instruction in 32 bits, and then Thumb2 was like, let's like still have 16 bits for some instructions, but 32 for others, and like we need a NOP for both. It makes sense, right? Like extra wide NOP is like really good. It's like a NOP, but like nothing, but like more, right? It's like a supersized NOP. And so the NOP in ARM v7, instead of being an alias for hint 0, was actually an alias for an idempotent instruction called move R0 to R0. So you're taking the R0 register and moving it to R0, which does, what does it do? Nothing, thank you. And so in Thumb, instead of move R0 to R0, you're moving R8 to R8. Equally useless. But what's interesting is the manual says this is, when you want to do nothing, this is what you put. The other idempotent instructions might do something. They might like actually execute or something, take some time. These ones, like, they won't. They'll just disappear. And so something funny is that ARM v7, if some of you are familiar with assembly, it also had condition codes on every instruction, right? So you have 32-bit of instructions. It's pretty wide, right? You can encode a lot of stuff. But 4 of those bits were a predicate on every instruction, right? So it's a static predicate, and you can mark instructions with that predicate. Now, the one at the bottom is always, right? So you always execute the instruction. But what's really funny is, this is basically how you encode if statements. If you have an if statement, it lowers to that. If you don't want to do a branch, you use you use those predicates, and it means that you could encode a conditional NOP if you wanted to in ARM v7, right? So it's a NOP that does nothing, but that might not execute, right? So if you say, like, if false, do nothing, basically it'll put a NOP in your instruction stream that just, like, disappear. It doesn't execute nothing. It executes extra nothing. It's pretty quaint. And so the condition has 4 bits of the 32-bit instructions, which seems kind of unwieldy, right? Because I told you ARM v7 had 32-bit instructions, but then Thumb2 has 16-bit instructions. Imagine they didn't use 4 of those 16 bits to encode predicates. That'd be fairly wasteful in your instruction encoding. So Thumb2, instead of having predicates, had something really cute. Does anyone know what it is? Thumb2 has this beautiful thing. It's really beautiful. It's called the IT instruction, IT, the if-then instruction. And here's how they describe it in the manual. It says, the instruction IT makes up to 4 following instructions. So like the instruction IT and the up to 4 after it, conditional. So you still give the IT instruction a predicate, 4-bit predicate, the same as you did for the 32-bit ARM instructions, and then you give it a bit flag of up to 4 instructions after this will be an if or an else. And so you have an instruction that can make up to 4 instructions after it either execute or not execute based on the predicate. Really cute stuff. Don't ask me what happens if you have 2 IT, one behind the other, one IT kind of covering another. Stuff happens. It's really exciting. But it means that you could have an IT block and then, like, 2 small NOPs and 1 extra wide NOP. Super exciting stuff. You could conditionalize your NOPs really well. Super exciting. All right. So earlier I said, like, the ARM v7 NOP, but like the pedants in the room, those who know assembly really well will come and say, actually, like, ARM v7 v6k variant introduced a true no-op instruction. Now, what's a true no-op instruction? Well, it's not an alias for a move. It's a no-op that will actually execute but still do nothing. Really amazing stuff. Really amazing. Like, they really needed, in the release note, you look it up, like, search for ARM true no-op. It has this true NOP. Like, they felt like they needed this thing. Super cool, right? Another fun fact this time about ARM v8, it has a 0 register, right? So it has a register that's a 0. So if you read from it, you always get 0. It feels kind of like a no-op. You get the 0. But if you write to it, the data that you write to it are just thrown away, right? So there's a register, you write to it, and it throws stuff away. So you can do computation or whatever else and put in the bit bucket, right? And so this is the description for the 0. There's actually 2 0 registers because ARM v8 was a 64-bit instruction set, and instructions can be 8, 16, 32, or 64. And so there's the XZR and WZR, or the 32 and 64 registers. They're actually aliases for R31, the last register in the integer registers, and they kind of alias and stuff. So super exciting stuff. There's 0 registers. You write to them, nothing happens. It throws away the result. Well, it can have side effects, like some of them can sub the flags. You can do an add and then, like, throw away the result, and that gives you just a flag test, stuff like that. And fun fact, it's kind of the same thing as writing to dev null, right? And those of you who are, like, POSIX familiar, there's dev true and dev false in POSIX. True, of course, returns 0. It's, as civilized people would do. True returns 0. And false returns 1, as civilized people do. But do you know that that's not always true? If you take dev true -- help and you pipe it to dev full, it'll be super exciting. Super exciting. You should try it out at home. Not here. We'll just keep moving. So one thing I like about computers is that there's really many things to discover, right? We have a wonderfully unreasonable people who pour insane efforts into designing modern computing. And it often feels like magic, right? Stuff I've been telling you, super magical, little stars twinkling and whatever. And so knobs are just really a tiny part of this whole thing. And I find that really exciting. I like this quote because, sometimes magic is just someone spending more time on something than anyone else might reasonably expect. And I think that's really delightful, right? And I think a lot of you in the conference kind of had that feeling as well. Right? So look at us programmers, and computer designers. We kind of think we're really clever, right? We're really exciting. We're a programming conference, super cool. But we have our nothingnesses, and we're like, we have the nothings. Very exciting. And I gotta be honest. Computing has only been a thing for 60 years or something. Artists have been at it for way longer than we have, right? So. You know the concept of a blank canvas, right, in art? And it's all about the nothingness, the blank canvas. And apparently, here's an example. Sai, who painted that? I'm not sure, I'm sorry. Okay. But so apparently, the critic at this exhibit of White on White said this was the best piece in the exhibit because something could be done with a blank canvas, right? So nothingness is so controversial, it goes to an exhibit and people just dump on it. It's great, right? And there's a lot of art like this that tries to go in nothingness and exciting stuff like that. Okay, so we can feel smug because artists have been doing that, but our brethren, the mathematicians, have been doing nothing for much longer than we have, right? So the idea of zero was invented mathematically, right? So here's the history of zero. It's a beautiful history. I think we all studied that in school. So the Babylonians did stuff about zero. Then the Indian mathematicians did stuff. Islamic mathematicians. Fibonacci introduced zero. He was like, yo, these people invented this crazy thing. Let's put it in our stuff, right? He introduced it in the 17th century. More stuff happened. Central algebra, the 19th century. Zero became foundational in set theory and abstract algebra. I still don't know what set theory is, but it's okay. And in the 20th century, zero was really integral to computer science and binary systems. So really exciting stuff. And what's even cool is year zero is the thing, right? So it's cool. So we discussed Unicode's blanks earlier, right? So we had 25 blanks, if you remember. And that's the thing, but Unicode has also a bunch of zeros and a bunch of nothings and empties, right? So how many representations of zero and nothing and empties do you think Unicode would have, right? It has 25 white space characters, seems kind of ridiculous. How many zeros, nothing, and empties do you think it has? Try it out. Can I fit them on the screen? I mean, they'll render because they're not white space, but I have a pretty small screen here. Let's see what it's got. So here's the first page of all those zeros, nothings, and empties that I could accumulate from Unicode. And it's really beautiful. I read some of them, I have no idea what they are, right? So there's the empty set, the reverse empty set, the empty set with overbar, empty set with small circle above, empty set with right arrow above. What are the mathematicians doing? Clearly nothing, because that's what they're doing. And there's null, and there's objects and digits, zero, and full width, really big zero, superscript zero, subscript zero, circle digit zero, negative circle digit zero, circle zero with a slash, mathematical bold digit zero. They have all this stuff for nothing. Isn't that exciting? Yeah. And so here's more. Vulgar fraction zero. That's cool. Super vulgar. Mathematical double struck digit zero. Arabic indic digit zero, comma. What? A bunch languages have their different zeros because of course they need their different zeros. It makes a lot of sense. And then there's a bunch more. So this is all the ones I could find. I'm sure I've missed some, right? And I've tried to render all of them. Not all of them render really well, but there's a bunch of extra stuff here. It's great. Ideographic telegraph symbol for hour. There's a zero in it. It doesn't make any sense, right? But we have zeros everywhere and nulls and empty sets and stuff like that. Super exciting stuff. Okay, so others do nothings, right? We had artists doing nothing, French doing nothing, we had mathematicians doing nothing, but we, computer scientists, we do it clever. We do the zero really clever. So I want to tell you about a load-bearing knot. Who knows what a load-bearing knot is? You know what a load-bearing beam is, right? Right. So in a house or whatever, probably the two beams, one beam over there is holding the whole thing here. If it collapses, the whole thing collapses, right? So for folks who've done performance tuning, there's this concept of a load-bearing knob, like a structural beam, like this beam right there. And if you remove it, the whole performance can change drastically. And in the case of knobs, if you add a knob, the performance can also change drastically. So you can change code a little bit, and all of a sudden it might get you a huge performance gain, give you 30% faster or something like that. So the concept of a load-bearing knob is super exciting. So it sounds counterintuitive, but it's all about often like aligning the micro operation cache, right? So that's like where people use this term the most often is I got to align the micro operation cache. So if your instruction happens to be aligned just right, and in some CPUs, the CPU front end doesn't stall. It won't be like, I got to find something else to execute. What do I do, right? So you align the instructions just right, and it won't need to go to the cache and fetch stuff. Right, so it has another cache in front of the cache that has a bunch of instructions already in there, and you want that cache to be really hot. Right? So that hitting that cache just right can dramatically boost the performance of your code. It's kind of like, has anyone ever moved houses or moved continents or something? Right? If you move and you fit everything in one truck and then you leave, it's pretty fast. If you got to pack 2 trucks, right, and you drive over there, you come back, and you're going to drive over. Takes a while, right? So that's why caching is really important. If you don't hit that cache line just right, it's kind of like having to move with 2 trucks instead of just 1 truck, right? It's intuitive if you see it that way. You save it a lot of time if you hit that cache just right. And so CPUs kind of fetch and decode chunks of instructions at a time. They'll look at a chunk and they'll decode it, fetch it, and figure out what to do with it, not just individual instructions at a time. That's why hitting that decode cache is really important. And in Intel, for example, people will have lore that says like, oh, the micro-op cache holds at most 18 micro-ops per 32-byte windows or something like that. And you have this little cache in the hardware, and like people who tune performance know exactly how to write. And the way they do that, say they have a really tight loop, is they align the instruction stream so that the decoder will start at the start of the instruction, and then the loop will go back to that. And so you'll always be in the cache. You'll never be redecoding after that, right? So I've tried to illustrate that. You have a little 32-byte window, and if you fall across the boundary, that's when you're moving with 2 trucks instead of just 1. Right? So you've missed your cache, and then the micro-op cache will need to come back and redecode stuff, right? So you use NOPs to pad that so that your instructions always fit in that window. All right, so I have an example from the Intel optimization manual. They have a really cool optimization manual that explains a lot of stuff about how each architecture works. Now, keep in mind, what I have here is specific to that CPU architecture that they're describing. Obviously, the Intel optimization manual won't apply to ARM, for example, right? So, differs by CPU. So really interesting stuff. If you want to do tuning, the load-bearing NOP is what you want to look for. Another place that you might find NOP is to align code to pages as well, right? So I'm talking about here just the decode window, but pages tend to be like 4 kilobytes or something like that, maybe 16, something bigger, 64. And you might align that to code pages so that different processes can share code as well, right? So you might have NOP padding so that one process can share the code that another process has and stuff like that, right? So if you look in like a dynamic library or something, you'll end up having some NOP padding sometimes or things like that. Okay, so let's move to other stuff about x86. So I was talking about ARM a bunch earlier. I've got some x86 here from Intel. Here's a bit more about x86. So how can, like in x86, like ARM was 32 bits per instruction, x86 really shines for NOPs because it's not 32 bits per instruction. Instructions like can be 1 byte, right? So it's pretty small, and then it can be bigger. So it's an instruction set that's more complex than ARM is in terms of how it's encoded. It's a variable length instruction set that's variable length aligned. And so alignment for ARM is not that tricky, right? You look and you're like 32 bits, 32 bits, 32 bits, that's an instruction, that's one, that's one. If I give you a stream of Intel instructions, I don't tell you where it starts, you can't really tell where the instructions start. And so that's where NOPs become useful because those instructions are all variable length back to back. And so if you want to hit a certain alignment, it becomes much more useful than it is, say, on ARM, which is a fixed width encoding. So given what we learned about like chunked encoding and instructions, cache streams and stuff like that, it's kind of important to align x86 instructions to keep the decoder happy. Right? So something to know is like it's encoded with variable width, but those instructions can have prefixes. Right? And so here's the list of all the prefixes that exist in Intel. There's a handful of them. It's like a prefix menu or something that I put on screen here. And so the prefixes are bytes that come before an instruction that modify what the instruction does. Right? So repeat if not 0, repeat if 0, segment overrides. There's different segment overrides because they have a lot of segments. And then operand size override and address size override. And that changes what the instruction after it does. Right? That's what a prefix does. So a fun fact about x86 prefixes is that you can have multiple of them on a single instruction, right? So where am I going with this? How many bytes does it take to encode a NOP on x86? Anyone know? 1 byte. Great, thank you, Robert. And you could put the NOPs back to back, just nop, 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 or you could use prefixes in front of them. Right? So here's Intel's own recommended NOPs. Right? So this is the best of NOPs directly from Intel. The creator of x86 says, they're the best NOPs. The ones you should use, those ones. And so if you look, of course, the NOP, 1 byte NOP is just 90, the encoding for it, but then you put a 66 in front of it, and then you have like a 2 byte NOP, and so on. You have a bunch of other stuff that encodes different types of NOPs. And you might notice that the 2 byte NOP uses the operand size override prefix, 66, and then instruction 90, which is the 1 byte NOP encoding. Right? So that's a 2 byte NOP. And then you look after that, and all the 3 and 4 and 5 byte NOPs don't have that instruction 90 in there. Right? So 90 happens to be the instruction, and I think Nicole said this earlier, exchange EAX, EAX, right? So you knew that. You'd seen the slides in advance, or you just know Intel assembly. So 90 is exchange EAX, EAX, which does nothing, right? But you could put other prefixes in front of that, but Intel decided that multi-byte NOPs would be the instruction with 1F instead, right? So they just have different encodings for wider and wider NOPs, and you can see that there's immediates that are bigger and bigger because it changes the operand encoding, right? Beautiful. So these are the ones that Intel recommends that you use. Now, I told you earlier the instructions have multiple prefixes, and some of them do, right? You see that some instructions can have multiple prefixes, but you're wondering, like, okay, well, you have from 1 to 9 length NOPs. Is there any more, right? What's the maximum size of an instruction on x86? Anyone know? 15 bytes. Thank you, Sai. Great job. Good job. I'd give out rulers or something, but I don't have anything to give out. So. And so the maximum size of an instruction on Intel is 15 bytes, and you can use the same prefix over and over again. And you're looking at this table, you're like, well, 90 is the first one, and then I have up to 9 byte of instructions. Is Intel hiding anything from us? Like, are there secret NOPs they don't want us to know about? Well, Intel doesn't really recommend longer NOPs, but who else could recommend longer NOPs? AMD. So we turn to AMD, and we're going to see recommended NOPs that are longer. Very exciting stuff. So AMD recommends longer NOPs by just stacking the 66 prefix in front, the operand size override, in front of the 9 NOP bytes that Intel recommends. It doesn't seem very exciting, right? So the 10, 11, 12, 13, 14, 15 NOPs are just the 9 NOPs with the 66 in front of it. It's fine. It's not super exciting, but actually it gets a bit exciting. They have this other thing where they're like, well, some of our old processors don't like when you repeat prefixes. And so here's double NOPs. If you want to do like longer NOPs, use these ones instead. It's 1 NOP followed by another NOP, and our older CPUs will like that better, right? So they have their special list of preferred NOPs as well. I don't know if Intel likes those NOPs or not. You can look it up on the internet. I'm sure if you ask ChatGPT, it'll tell you the right answer. So the Linux kernel also knows about long NOPs, right? So Linux only knows about 11 of the NOPs, right? And so this is literal code from the Linux kernel. I've just compressed it a little bit. It's beautiful. Like, look at the naming convention for those macros. It's really nice, super creative. Bytes NOP 1, bytes NOP 2, bytes NOP 3. It goes up to 11. Nice. So there's plenty more fun on x86 too. Like, I talked about NOPs, but there's a pause instruction. What do you think the pause instruction does? It's actually a NOP with a repeat prefix in front of it. Remember the prefixes? There's a repeat prefix. If you NOP twice, that's a pause. It's beautiful. It's really cute. F390, great. And repeat instruction, like I could spend so much time on the repeat instruction. There's a return instruction on Intel, and you can repeat return. It's so beautiful, super exciting. Anyways, there's so much good stuff on Intel, it's great. Oh, okay, so by now, I think you all appreciate nothing. Right? And really, like, ancient philosophy had that before us, right? They'd been at it for a super long while. I think it's kind of human to appreciate nothingness. We have this abundance, and then you go back to nothingness, like, yeah, it's kind of nice, right? And so Marcus Aurelius here has said, very little is needed to make a happy life. It is all within yourself in your way of thinking, right? So really embrace the NOP in life, right? And I have another quote from a famous philosopher here. Tell me if you recognize who it is. I mean, the name's going to be on the screen, so it's kind of easy. But train yourself to let go of everything, your fear to lose, right? Yoda. Super famous philosopher, really solid stuff. Nops are everywhere. It's beautiful, right? Ancient philosophers had that too. Now, I want to talk about the alpha nop, right? Now, you're all wondering, whoa, what's going to happen? Because, like, alpha nop. There's a nop that's, like, better than the rest, like top nop, the alpha nop. Nah, I mean the defunct DEC alpha instruction set. It's an instruction set from the 1900s, for those of you who remember. I know saying 1900s is great, it's beautiful. But it's an old instruction set, and it had a cool thing about nops. So here's the nops that it had. It defined three nops, the U nop, the nop, and the F nop. Right? So the UNOP is just a load quad word unaligned. The NOP is a bitwise inclusive OR that does nothing. And the FNOP is a floating point copy sign from the floating point value to the same floating point value. So it does nothing in floating point. Really beautiful. Now, I said there's three NOPs on the alpha, but that's not quite true. If the clever people here are people who have programmed in alpha, people who programmed assembly in the 1900s, one thing that you should know is that R31 is a special register that's like a zero register, which is why this works, right? So it's kind of like a bit bucket. If you write to it, nothing happens. Sounds familiar? ARM copied that, right? So Rx, though, is special here. It has 32 encodings. This is 32 registers that are encoded in there, and Rx can be any registers. Now, the thing is, alpha defines three NOPs, but if Rx is not R31, the bit bucket, it's unpredictable what happens on alpha. Right? So it might cause an MMU exception. So it might trap. So there's a NOP that has undefined behavior, and if you run it, it might just like trap. So it does nothing-ish. It's really beautiful. So I mentioned floating point NOPs on alpha, and I'd be remiss if I didn't go back and say Intel also has a floating point NOP. Really exciting stuff, right? So I have the Intel instruction manual declares it here, D9, D0. It performs no FPU operation. This instruction takes up space in the instruction stream, but does not affect the FPU or machine context, except the EIP register and the FPU instruction pointer, right? So you just point to the next instruction instead. Really exciting stuff. A NOP that floats. It's really beautiful. And really, like, looking at all these things, it makes me think, like, we've invented all these instructions and these instruction set architectures, and they all have these fascinating different nothingnesses. And as I was saying earlier about French, like, human language does that too, right? We have a bunch of other things. Nothing, zilch, nope, diddly squat, rien, pantoute, trois fois rien, zéro pinot. I'm from Quebec. The French people will hate this. Nada, we have mu, nani monai, zero. Yeah, there's a bunch of NOPs in every single language that exists, zeros and everything else. But like, if you think about it, I talked about like the comma and the space and the em dash, they're NOPs. But in human speech, we also have nothings, right? That doesn't mean anything, right? It's also a NOP in speech. Think of human language like that. Language is full of these things. And what's really cool, as I was researching this, there's a study I read a long time ago that I found again while I was researching this, and I thought it would be great for this talk. There's a study called A Cross-Language Perspective on Speech Information Rate. Has anyone read that? Or at least read it on the internet? Or you can read the summary on the internet. And so the conclusion of that study was that languages which are spoken faster tend to encode less information per syllable. So the conclusion of the study is that the information rate is similar on every language, but some languages are faster than others. And so that's kind of interesting. Let me give you a few examples. I'm going to go from low to high information density, right? So in Spanish, you might say, hola, ¿cómo estás? Hoy es un día muy bonito, ¿verdad? Right? So it's a lot of syllables, 24, which just means, hi, how are you? Today is a very nice day, right? So it's a lot of syllables to just say a few things. Now, in Japanese, you might say, ohayo gozaimasu, kyou wa ii tenki desu ne? Right? So it's kind of a lot. It's 22 syllables, and it still means the same thing. Good morning, weather is nice today, isn't it? Then in French, you might say, bonjour, comment vas-tu? Il fait beau aujourd'hui, non? Right? So it's still pretty long, 18 syllables, right? But still saying, hello, how are you? It's nice today out, isn't it? And then in English, you'd say, good morning, nice weather today, huh? 10 syllables, shorter. But the information density, the amount of time it takes to take stuff, the amount of stuff you're saying, according to that paper, is about the same per language, right? So now, whether you believe that study or not, I kind of like it. There's something compelling about it. Whether it's true or not, I don't really care, right? So I'd say that from that study of languages and the bit rate that you have, there's kind of a parallel to instruction sets, right? So I've talked to you about ARM and Alpha and x86 and stuff, and I kind of think like the reduced instruction set architecture, RISC versus CISC versus VLIW, they each have their own encoding quirks, and the way they're encoded is different, but I think they all have some amount of redundancy encoded in them and fillers in them. And you could count the knot density of a program for different instruction set architecture. Right? So I think in that study, Chinese was the fastest language. I'm not going to do Chinese, but like, would you say that APL, the programming language, is just like random, like cat walking on your keyboard, is kind of like Chinese, like super information dense? And would you say that like Java or COBOL are kind of like those languages that take a lot more to say less? Now, I chickened out of APL because I just can't speak APL, but whatever. So I thought it was pretty cool. So we touched on hardware a little bit, and we'll do a little bit more of that. So earlier, I mentioned the phone in your pocket and how they're doing nothing. Well, usually devices with battery power down when they do nothing, right? So my phone is probably mostly powered down most of the time. It's just there doing nothing, right? They power down. So what do they do when they do nothing? They like play little games or something? Is that what hardware does? Well, the OS monitors activity, tells the hardware to power down, and there's multiple power stages, and like it'll wake up from time to time and like check email and text messages and then power back down. Try to bundle everything into one batch to go back to sleep really fast. So hardware gets pretty good at that. And some newer hardware have like efficiency core and power cores to do nothing really fast or nothing really slow because it needs to trickle energy out, right? So imagine you're executing NOPs. Some of them execute super fast, and some of them execute like kind of slower but lower energy, right? It has a side effect of energy usage. Right? Maybe it's more like this, right? OSs kind of batch work, and they do like the little frequency. They wait, and they power on like the Wi-Fi and the cellular, which use a lot of energy, so they want to batch stuff super efficient, right? And there's kind of a reverse problem also. I was talking about how like you might want to use low power, but like with new data centers, like you don't want to stop using power fast also, right? So a lot of the kind of bigger data centers, if they're drawing a lot of power to, say, doing like a bunch of AI workloads or something like that, like they have thousands and thousands of GPUs just consuming power, and then they're done. You can't just stop consuming power because that's not how the power grid works, right? So power grid can't handle a bunch of things coming offline at the same time. And so those data centers have to kind of wind down their power usage slowly, and so they do a bunch of fuse, multiply, add or something to do nothing to be able to power down. So there's a side effect to doing nothing in this case, which is very exciting. Right? What's that? Anyone know what that sound is? Okay, so hardware, but physical hardware. This is the sound from the Montreal Metro. And so the Montreal Metro initially, it has a chopper controller in the original Metro. That sound, the 3 tones, is when the chopper controller for the Metro going away, like leaving the station, kind of has 3 modes for powering up. And that sound became the sound of the Montreal Metro. So it's an accidental side effect. It's just like the sound it makes when it powers up to like leave the station. It's an electric thing, just goes, right? It steps up the chopper controller. That's a side effect that kind of does nothing, but the sound itself is really cool. And so as a kind of kickback to the original sound, the newer Metros don't do that sound anymore, except they have speakers that play that sound when the Metro leaves, which is really cute. And so like, imagine this existed for nothing. It was a side effect, an accidental side effect, and everyone was like, that's the sound the Metro makes. It was like, I grew up, I didn't know that was just an accidental thing. It's really cool, right? It sounds like nothing, it's beautiful. Okay. Music. It's beautiful, right? So this is a piece, 4:33, John Cage, identified correctly by Sai here. It's 4 minutes 33 of nothing, right? It's really beautiful. I just played it for you. I hope you appreciate it. So we've seen nothing in assembly, and I want you to think now, can you express nothing in your programming language of choice, right? What's the best program that does nothing that you have? Think about it. Right? What's your favorite program that does nothing? Let's ignore assembly now. Let's like, you were saying I needed to do C++, right? So like, here's an easy program that does nothing. It's really beautiful. a little frame around it. It's just a semicolon. It doesn't do anything, right? You can just like put a semicolon, it won't do anything, but like pretty exciting, right? Here's another one that's really beautiful. Just little empty braces, right? So I'm going to have empty braces here. Doesn't do anything. Beautiful. Okay, nice. Anything else? Here's an empty program. This is the International Obfuscated C competition winner. Int main, paren, curly. Doesn't do anything. Beautiful. Like an award-winning nothing. Isn't that awesome? Here's a bunch of others. We talked about idempotent instructions before. You can write that in a programming language like C, C++, whatever. Those don't do anything, right? The value is no different before or after the instruction. Doesn't do anything. Cool. This program does nothing. All right. So I was talking about this with John Reger a while ago. I started writing this talk 8 years ago, and I was talking to John at some point, and he mentioned that he had a super optimizer that searches for all idempotent instructions on x86. He wrote a super optimizer, right? So he's a professor. It's okay. But I kid you not, he sent me 679 NOPs from x86. I'm showing you like 16 of them here, but he sent me 679, and he just killed his program after a while because it was searching for all the nothingses in x86. Super exciting stuff. And some folks like really have fun hobbies, and I really love it when I bring up something completely ridiculous like this talk, and someone goes and says, "Oh, well, actually, I'm a world expert, the foremost expert in the world on this ridiculous topic." Can you imagine? Like he already had that lying around, just sent me like a link. It's there. You can go check it out. So moving on, you can do a thing and discard a value. It's not just semicolon, 1 + 1, semicolon, discard, throw away, beautiful. You can do math, square root of 42, floating point, just like throw that away, it doesn't do anything. And the last one is cool. So use strict, that works in C++, right? Doesn't do anything, just like quotes. In JavaScript, it does something. It changes the mode in which JavaScript evaluates. Beautiful. Beautiful. I said it mentioned JavaScript. Here's another beautiful one in JavaScript. What does this do? This is the sarcasm mark in JavaScript, right? /s, sarcasm. Just write that in your browser or whatever. Try it out. It does nothing. Sarcasm, nothing. It's beautiful. And other languages have like doc strings in Python. You can do that in C++ as well. You have to use the R in front of it, but like it doesn't do anything. You can call empty functions in C++. Square brackets, round braces, curly braces, parentheses, beautiful. You can do that with like classical avoidance also if you want to have a nice little lambda. But like the compiler just gets rid of all of them. All of them, they're just gone. It spends time on them, so it has a side effect. The compiler's like, oh, what is that? Just throw it away. Just throw it away. And like, it's kind of cool, right? The compiler generates code and then throws it away. Nice. And here's code that does nothing, but like in a complex way. So the code I have here purposely generates code that does nothing, because it's hard to get the compiler not optimize away your nothingses, right? So I wrote code here. This is my little compiler explorer emulator, and like this is beautiful x86 code that does not, ARM code. Wow, okay, and it doesn't do anything, but like I forced the compiler to generate nothing. It's really nice, super exciting stuff. Right? So let's take a quick break and admire like what computers can do. Right? So this is a cellular automaton. Is it nothing? What kind? Is it art? I don't know. Some people use them for random number generators, really exciting stuff. But they're really beautiful. This is a game of life, right? It doesn't really do anything. It's nice to look at, though, right? So it doesn't do anything, but like you can do a lot of really big, complex nothingses, okay? So quiz time. What's the longest NOP? I asked people before the talk, like, what do you think the longest NOP is? Come on, you've had like 40 minutes to think about it. So who's familiar with the Z80 processor? Jason? No, not really? Yeah? Okay. So the Z80 was a super popular processor from the 1900s, thank you, and it's super popular with retro computing people. And what's interesting is it has a 16-bit program counter in the Z80 with a 64 kbit address space. And so the longest terminating does nothing overall sequence is this. I'll pop it on the screen any moment now. The Z80 is really slow. So the longest do-nothing sequence is 65,535 bytes of DD or FF followed by a single 00. Right? So you can have a NOP that's this long, super long, 65,535 plus 1 byte. That's a super long NOP. Right? Isn't that exciting? You can burn that many cycles. It's about like 0.02 seconds on the Z80, 3 megahertz of just nothing. Super exciting. Anyways, I have some more principled nopping. So this is a loop, right? Everyone's written a loop like this. What does this do? Is it C or C++? It's obviously nothing, right? It's just like looping. It doesn't do anything, right? Oh, Here's another loop. Here's another loop. What's this one do? It's tricky. There's a difference between the two. The one on the left is C. The one on the right is C++. C is an infinite loop. C++ is undefined behavior. So if you look at this Godbolt link, main parens while true semicolon, close brace, and then a completely unrelated function. Unreachable. It's not, I'm not calling it, and this will print hello world. Go to the Godbolts, if you don't believe me, it prints hello world. Nice. Undefined behavior, nothing. It's really cool. Actually, I lied. The internet got really angry at this a while ago, and I wrote a paper to fix it. So in C++ 26, the C++ behave in a sane manner, which is completely ridiculous. Just don't read the paper, it's horrendous. And so here's a bunch of nothingness. I like to think of things in terms of Dungeons and Dragons alignment, right? So I think like, is this good, evil, like, you know, things like that. And so I think like the while true is kind of the true neutral of infinite loops. What about these ones though? Like these are kind of like still pretty neutral, right, in terms of what they do. The for with the semicolons though, it's kind of like it's got little fangs, right? So it's kind of lawful maybe. It's kind of the while true nothing. Still undefined behavior in C++. Thank you. Those are just weird. Like I don't. How does this even code? Const expert with like whatever. I think they're kind of pedantically correct loops though. So I'd say they're kind of lawful in that like they're pedants about it. These ones are just weird. I don't even know what they are. Like it's. When I wrote the paper and we talked about infinite loops, you wouldn't believe the stuff that came out. I don't even understand how we do this. This one, though, the while true stood this thread yield is totally lawfully good. Nobody writes this code. I'm probably the first person in the world to have written this code, but it's lawful good because it's the right way to do it, which nobody does. The go-to one, beautiful, though. I love it. And this one, like you can use like a set jump, long jump to do a loop. Isn't that beautiful? It's really funny. Yeah, and so look at that. This one doesn't even have a loop construct, but it loops forever. What I'm doing is I'm setting a signal handler and then calling abort and then looping back and looping. Is that undefined behavior or not? I asked the people responsible for this, and they didn't know and they didn't fix it. So it might not be undefined behavior or not. But like I'm just aborting and going back, aborting, going back. It's really beautiful. And here's another one that I really love. We talked about alignment. This is a fork bomb, really great sort of loop. Right? Does it do anything? Not really. It burns your CPU, right? It starts processes and stuff and kills the previous one. It doesn't really do anything. It just goes around. Super cool way to do nothing, right? So let's get back to the basics and do nothing with just comments, right? So no code comments, just like true neutral stuff. So I had a semicolon. That's kind of true neutral, like you don't have a comment. Then you have slash, star, really nice types of comments. Everyone's written code like this before, right? If false or while false. You're trying to debug stuff. You're like, it's just like this whole block, whatever. Right? You want it to still compile, but it's falsed out, whatever. If zero, end if, it's kind of lawful neutral, lawful good. You're supposed to do that, right? Here's another. Has anyone ever commented code with a goto to just jump around it? I mean, like it's not a bad idea. It's kind of chaotic neutral, but like you could do that. It's cool. Static assert true comment. That's kind of chaotic good, right? It's like whatever. It's just do stuff. This one, I love it. So this is a GCC extension, the statement expression, parentheses with curly brace in it, and you go to from the if statement outside of the if. Chaotic neutral, beautiful, I love it. But the last one is even better. You've probably seen it on the internet. This is the power comment. You use the asm statement with a /* and then a */ afterwards, and this comments out what's in the middle because the assembler just like takes it away. It's beautiful. Look at this code. Like I don't think you fully understand. It prints hello world, not hello cruel world. It makes it all the way to the optimizer, and then the optimizer looks and says, oh, well, like I'm just going to emit that, gives it to the assembler. The assembler says, that's a comment, throw it away. Nice. Nice. Yeah, it works. Try it out. So comments are nice and all, but what could more nothing than parsing be, right? Like C++ defines parsing. And it has this concept of unevaluated stuff. Are you ready for this? Because C++ is, this stuff is unevaluated. If it's not evaluated, it doesn't have a side effect, doesn't generate code, right? So first unevaluated thing in C++, size of expression. That doesn't do anything, right? Well, except in C. In C, if it's a VLA, this does something. N is equal to 2 after this expression I have here. Robert, did you know that? Convener of the C committee? Yeah, it's beautiful. It's amazing. Size of ... pack evaluates the size of parameter pack, does nothing. It's great. A line of with type ID doesn't do anything also. It's not evaluated, but it creates a value at compile time. Type ID expression, also unevaluated context, except it'll do something if like there's a polymorphic class type, in which case it evaluates to get the dynamic type and may throw bad class type ID if you do reference a null pointer. So it's unevaluated mostly. It happens, it's mostly unevaluated. Decal type doesn't do anything. No except doesn't do anything, or doesn't generate code. C++ constraints, concepts, all of these are unevaluated. The expression immediate, the expression that appears after the requirements body. And so C++ 26 is supposed to have contracts. I won't talk about them too much, but there's a mode where you can say ignore the contract. And so you have a whole contract that you just ignore. It does nothing. It's really great. I love it. Semantic nothings, right? So for those of you who like to have fun, who's read the C++ standard cover to cover? Yeah, so there's this thing called the abstract machine. You have, nice. I even believe it. And so there's this thing called the abstract machine in C++, right? And so it's towards the beginning, and so it's a description of what C++ does, how theoretically C++ works. And I have the explanation here. So theoretically, there exists a pen and paper C++ abstract machine. You can get paper, like there's paper over here. You could just go and get paper, get a pen right there, and you could, like C++, like evaluate the abstract machine one at a time. It's super exciting. In theory, you could do that. Richard Smith is probably the only person who does that for fun. But like, it basically is kind of a Rube Goldberg machine that does stuff one after the other. And you could have a whole abstract machine where you're like, oh, I have this comment, this infinite loop. Let me note that I did nothing. And you have like this kind of bookkeeping you follow and whatever. So you could like be a person evaluating C++ and appreciated the nothingnesses that are in it. That's really beautiful. So let's go back to math a little bit. So earlier we talked about mathematical zero, but do you know how computers represent values, right? Like integers? Robert, do you know anything about integers? It's Robert's hobby horse, just like I'll stop. So integers can obviously be zero, but we talked about that earlier. They can also be minus zero, right? So you can negate a value, including zero, and have a minus zero. Now, as of like a while ago, C and C++ only admit that 2's complement exists, and so it doesn't do anything, right? So that negative zero is negating a thing that's already nothing, but doing nothing in its own, because there's only one type of zero in C++ and C. But in floating point, back to floating point, we love floating point, there's a sign bit, and so there's 2 zeros in floating point, right? Is that true? Is there just 2 zeros in floating point? Yeah, it's very small things. Just like, what if you're really close to 0? Is that a thing? Subnormals. Subnormals are exciting. So subnormals are this thing in IEEE 754, which is like really, really close to 0, but not quite, not quite. And there's 9 quadrillions of them in floating point 64. Really exciting stuff. And subnormals used to be slow on hardware, still kind of slow on some hardware. And so there's flags like denormals are 0 and flush to 0 that make them 0. Right? So you get a denormal and then boom, it's 0. Right? So there's like quadrillions of zeros that exist in floating point. Now, math geeks are really upset when you say that, because there's like this thing called gradual underflow that's really valuable for some mathy reason I don't understand, but whatever. Let's move on to nans. Who knows nans? It's a number that's not a number. Isn't that exciting? Like, there's 2 zeros, there's all these subnormals, quadrillions of subnormals that do nothing, and then there's numbers that aren't numbers. And there's also quadrillions of them. There's silent nans and signaling nans and other stuff. And there's even this thing, like JavaScript implementations love this thing called nan boxing, also Lua implementations. You can have whole JavaScript objects represented inside of a nan. There's a whole world in there. It's super exciting stuff. Look up nan boxing, it's great. Okay, so you're still here, nice. So let me tell you a fun one, NOP sleds. I had a question at the start, am I gonna talk about NOP sleds? I'm gonna talk about NOP sleds. What's a NOP sled? It's a knob that slides, right? Yeah, so you love fun things, NOP sleds. So JavaScript went, I wanna be fast, like in 2010 or something. Everyone was like, JavaScript's slow, me be fast. What happened? All the compiler engineers, myself included, were like, nice, we can make stuff fast. What happened right after that? Hackers went, nice, you want to be fast? You're going to have some bugs. And yeah, like, so there's this, oh no, my animation's dead. Oh, my NOP is broken. So hackers went and said, nice, I'm going to be fast. And so they created this thing where they inject a bunch of NOPs inside the instruction stream, and then they have the exploit at the end. And usually hackers can't just say, jump over there, so they just fill up the instruction set that JavaScript generates with a bunch of NOPs, which slides them to their actual payload, their actual exploit. Really exciting stuff. So Sometimes there's stuff you wish you didn't know. There's this thread on the binutils channel, on the binutils mailing list. I'll jump over because it's really terrible. But like there's a whole buggy knob in one of the MIPS implementations. So you think knobs don't do anything. There's a knob that's buggy, like my slides, super buggy. Anyways, there's an erratum on it. So there's a knob that does nothing, and so binutils comes in and fixes the knob for you. Right? Another thing, optimal knobs. What's the best optimal knob that you can have? The fastest knob. Is there a fast knob? There's a whole paper about fast knob, but Linux has got you covered. Linux has this code in it that's like, you can look it up, this is real code from the Linux kernel, that tries to optimize what the knobs are. Right? So it goes and it says like, hey, like I'm going to give you some really optimal knob and whatever else. Really exciting stuff. Okay, what else is there? So I'd mentioned magic, and I guess like the point of the talk is that it's really delightful that you can find things in the smallest, most niche places, right? Computer knobs are one place like that, and sometimes magic is just someone spending more time on something that anyone else would find reasonable, right? And so like, with AI and stuff like that, like the big picture is really easy. You can get 80% of the work done really fast, and then like the 20% still kind of matters, right? Like you do all this code generation and whatever, but the 20% getting that stuff really good still takes a lot of time. You want to do some magic. You want to delight people, right? Take this talk, for example. Like the whole talk, it looks like a TUI and whatever, but it's actually not. Like it's not a terminal. It's like I have theme switching and other stuff implemented. There's a lot of exciting stuff in this thing. Like you can like go ahead and switch themes and stuff like that. It's really cool. And this is kind of delightful. Like you want to have fun in life, right? You want to make beautiful knobs and make magic and whatever else, make people happy, right? So as tech evolves, I think we want to be able to do more and more magic in the physical world, not just in computers. And you should put more time than is reasonably that makes sense to create really magical things, I think. And maybe I think we'll create really truly magical nothings as well. Okay. So that's my talk. Thank you. Any questions?
79, but I'm way low.
79? Like you counted?
I was counting knobs, but not nothing.
We had quadrillions of them, is the answer.
Yeah, you said quadrillion here,
Yeah.
and I gave up on that.
Yeah. And like the Z80 has like 65,000 of them.
I skipped that.
Yeah, you got to count all of them. All the Unicode ones, I had like 3 pages of 25 lines each of knobs, and like, yeah, there's a lot of knobs in life.
I guess I'll say like you said JavaScript knob, but
JavaScript knob, yeah.
yeah, but when I was always thinking like Intel knob in the 90s, because what attackers will do is they'll write an exploit, but maybe you'll have some randomization, and they won't know what address to jump to, and so they just write a ton of knobs.
Yeah.
Now they just have to hit the side of a barn with a branch.
Yep. Yeah, so the way, so the paper Attacking Client-Side JITs by Chris Rolfe and I forget the other guy, it's at Black Hat 2010, I think. It details how they attacked, I think, Firefox originally, but they ported that to Chrome also, to use the JavaScript properties to be able to predictably inject instructions in the instruction stream, which like JavaScript doesn't allow you to do that, but the way JITs optimize stuff is they had an inline cache, for example, and that inline cache was sometimes attacker controllable because it would say like, oh, did you just see this double? Then like I'm going to put that in the instruction stream and patch the code at runtime and then do a special thing and whatever. And so they could have a special double that actually encodes a NOP or something like that, an exploit package, and then they would use that as a way to do stuff. And so randomization that you mentioned is one way that, because they didn't just say, hey, we hacked your stuff, they also had workarounds to those hacks. And so they had randomization to make it so that the JavaScript code gives you a double, but then you XOR it with a random value that decided at the start of the program, so the attacker doesn't know what's in there. Right, so the idea is the attacker is in JavaScript land and gets to generate stuff there that they know, right? But they don't know where it is, and they just say, jump over there. I can't see, but I put some stuff there, and I'm going to slide to my exploit by having a bunch of NOPs. And so if you randomize stuff, well, you can't predict what the instructions will be. So there's a bunch of, I think they had like 11 countermeasures or something. It's a really cool paper. Not particularly relevant anymore, but really cool. All right, thank you.